Hi everyone. Good morning, good afternoon, good evening, wherever you are. My name is Victor Odari from Masinde Muliro University of Science and Technology, and I also happen to be a co-chair in the upcoming AMRS 2026, which will happen in December this year at University of Nairobi, Kenya. So in preparation for the conference, we usually have monthly webinars, and today we have one which will be done by Professor Cecil Ouma. I hope I'm clear. I hope I'm audible. Please confirm. Someone confirm. Cecil, can you hear me?
Yes, I can hear you.
Great. Thank you. I hope everyone else is able to hear me. So, in preparation for the AMRS 2026, we usually have monthly webinars, which are on the last Thursday of every month at 3 p.m. CAT, Central African Time, or 4 p.m. East African Time. So today we are glad to have Professor Cecil Ouma with us. But before I allow Professor Cecil to proceed, allow me to just share a slide of what we are planning. Mhm. So I hope you are able to see my screen. And yes, this is what we intend to have this year in December. That will be the 13th International Conference of African Material Research Society. So we shall have our pre-conference from 5th to 6th December, followed by the main conference, which will take place from Monday 7th to Thursday 10th. So this will be at University of Nairobi, and the theme of our conference is Material Science and Innovation, driving sustainable development and socio-economic transformation in Africa. We shall cover quite a number of themes, as you can see here: biomaterials and materials for health, materials for agriculture, materials for energy, materials for construction, building and infrastructure, nanotechnology, materials in mining and mineral processing, advanced materials, materials for manufacturing of materials and structures. And our talk is in line with our second last theme, according to the list here: artificial intelligence in material science. And we shall have special sessions. We have a special sessions by the UNESCO chairs, the African Light Source. We will have a special session on the AMRS, EMRS, and many more have confirmed to participate in our pre-conference, which we shall conduct between 5th and 6th. So you are invited to apply and come for the conference, register for the conference. Though we are still working on the website, in a few weeks' time, it will be up and you should be able to do so. So for today, I want to welcome uh, Professor Cecil Ouma. Professor Cecil Ouma comes from Professor Cecil Ouma comes from AIMS, Rwanda. So he is the academic manager at AIMS, RIC, and his PhD, he got his PhD from University of Witwatersrand in computational materials, and he also got his master's in an energy program from the same university, WITS. So today he's going to share with us part of his work. And with that, I want to welcome Cecil to give us his talk. Thank you.
Thank you so much, Victor. I hope I'm audible, and thank you for giving me the opportunity to share the ideas that I'm currently exploring. So just a little correction. I did my PhD at University of Pretoria, and then went on to do now a master's in energy leadership at University of Rwanda. So my background is in physics, and as Victor has said, I work for AIMS. So what is AIMS? AIMS is the African Institute for Mathematical Sciences. So I am a physicist working in a mathematical sciences institution, but we are often confused with an institute for mathematics. We are not an institute of mathematics, but rather mathematical sciences. So whichever domain you come from, where there is a mathematical sciences applications, be it computer science, be it physical chemistry, be it material science, be it engineering, be it mathematics itself, we always open our doors to you. And for us, we believe that an AIMS graduate is meant to train hundreds, just as one algorithm scales to millions. And that is why we are a Pan-African institute, we are a Pan-African network of centers of excellence. We were founded in 2003 with the mission to increase the capacity of faculty in African universities when it comes to mathematics and physics departments. And 10 years down the line, that aim was achieved. And then we transitioned to the theme of the next Einstein will be African. And in this, we were trying to find those thinkers wherever they are. We wanted to find them in the corners of the continent, which many institutions cannot be able to reach them. And when we celebrated our 20-year anniversary, we have now evolved our theme to focus mainly on the youth. And our motto for these coming 10 years is in African youth, the future of science. So for us, we like to move mathematics and the mathematical sciences just from being mere models to being tools of practice and standard practice. So we are informed by the irony we live in now, that despite the fact that Africa being the birthplace of mathematics, as evidenced by the Ishango bone, whereby it is the oldest artifact ever found in history that shows that early human beings also were doing mathematics. And the Ishango bone is the one that informed probability theory. It informed factorials, it informed prime numbers, and these are the tools that are running AI models that we are talking about today. So for us as an institution, we see the irony whereby it is the African continent that created the language, which is mathematics. And then others wrote the dictionary, like the Newtons, the Copernicus, and all of those mathematicians, you know, like Poincaré and whatever, when they give us calculus and stuff. But then now we as a continent, we are still now behind in that we are paying to translate, in that we are actually struggling to compete in this domain that we are the ones who give birth to. So we have forgotten to claim this inheritance. And as an institution, we are trying to find ways in which we can be able to evolve some of these theoretical concepts that we have interacted with. We want to evolve them into practice. So on we go with today's simulation. So today's simulation, I'm talking about the presentation. I'm talking about a gambit. I'm calling it a gambit because many people believe, because like the way material science discovery has been done in practice today, is that we have the person who is synthesizing, who is working in the lab. We have the person who is modeling or computing something, whatever, and then through that they concatenate, and then voila, they're able to discover a material. But then now, because experiments are becoming expensive and they're becoming laborious and time-consuming, and the materials configuration space being broad, we are seeing now the emergence of the North-South collaboration and South-South collaboration taking place, so that we can be able to exploit the resources that are there in the different institutions. But then now with computational simulations, it means that we are defying this paradigm. We are not constrained by this space. But then we are in a situation of overhype in that we believe that because algorithms have improved and then computation power has advanced, then we are able to do more calculations and then we are able to gain more insights. But then now came in the era of AI, and from AI we are evolving into what we call agentic AI. And this is what I wanted. I wanted like to pose some thought questions, provoking questions unto you, so that we are able like now to understand whether we are actually biting more than we can chew, or whether we are actually on the right track. So the main questions that I wanted to respond to in this talk is like asking the questions like, because computation and simulations have mainly been used for prediction, or sometimes explaining that what if we stop training AI to predict material, but rather teach them to discover new materials through simulated ecosystems. Won't we be able to discover materials faster or better? So this is the theme of my research that I've been trying to run for the past 2 years, because at AIMS, it is the only place we can be able to experiment with some of these ideas. And as, this is also informed in part with the projection that is already out there that by 2050, most of the world youth or the world youngest population will be based in Africa. And if you look at yourself who is on this call today, I want you to maybe count how many gadgets you have with you. I'm sure each and every one of you has a phone, and it is not just a phone, it is a smartphone. Some of you may even have two, one for work and one for personal use. You have a tablet, and then you have, let's say, a laptop, and then in front of you maybe you have this nice beautiful screen that you have in front of you that now scales your vision from the tiny screen of your laptop to that bigger one, you see. And then you have like, when you go to the house now, you have CPE equipment and whatever. All this is just gadget upon gadget upon gadget upon gadget. But now, if 50%, if by 2050, the youthful 40% of the youthful population will be based on the African continent, aren't you seeing that there is an existential threat when it comes to materials? And that is why we need to start searching and looking for ways in which we can be able to try to save this generation. And here we are seeing the emergence of a trap when it comes to our consumerism, because just as you did the count of all the gadgets that you have, now imagine we scale the current population, you and the youths that are going to be there, to 2015. How many gadgets will need to be manufactured? And then you find like the gadgets in itself is a value chain. It is an ecosystem whereby gadgets depend on are manufactured using electronics. The electronics are developed using materials. Materials are obtained from minerals. So with this accelerating gadget addiction that are mainly anchored on electronics, but then you look at the main source, which is the minerals. We are seeing minerals now is causing wars between nations. We are seeing minerals having a lot of geopolitical connotations. We are seeing depletion, especially when you do catalysis, you will hear platinum group materials that they are very scarce, and then we need to transition to these new energy technologies. So the question that we need to ask ourselves is material science of 2050. Is it the high time now we start maybe focusing on materials which are small but with large surface areas like morphs, or are there other materials better than morphs or similar than morphs that are still there that we haven't discovered? So why am I asking this? I'm asking this because we are constrained in terms of cognitive capacity or competencies within the materials innovations value chain, because some of the good scientists we've had are currently now retiring, and now we are facing a crisis whereby we have a lot of young people who are impatient when it comes to training. They will not want to go through the normal brick and mortar, and we are seeing even with generative AI coming into the classroom, we will soon have students who will not be able even to derive an equation. But then now we are seeing that now, if innovation leadership is located outside of the continent. And then they decided to charge a premium on this innovation. How will we as a continent survive the 2050, the 2050 youthful revolution? And that is why for me, I believe it is time for a Roger Miller moment when it comes to material science innovation. I apologize to those people who were born in the era of Messi and Ronaldo. But it is also a Google moment for you to go discover some of the people we had. Roger Miller has a famous dance when he danced at the flag, because like until Italia 90, world football had not yet recognized African potential. Until that game between Cameroon and Argentina. And when Roger Miller scored that goal, we find like there is a mindset change, and people started looking for Africa in terms of football in another way. And we see here, it's like Roger Miller didn't ask to be included in the soccer scene. He didn't ask to request for a film. He came to the scene and he performed what he did. He did what he was supposed to do. And he changed the narrative for the continent. And I believe as the generation of African Materials Research Society scientists of the day, we need to see how well we can also participate in these discussions, not whereby we are latching onto the successes of like North-South collaborations. We need South-South collaborations, and we need collaborations that are going to give us this moment. So we believe as an institution that borrowed tools, we cannot use borrowed tools to win anymore. That if we want like now to solve the gadget problem, we have to go buy and import technology from China, or we have to go to Russia to obtain ABCD, or we have to go to the US and wherever. We cannot be able to import all solutions, because if we import our future, then it means that what are we creating as a society? And this is what I say, it is a moment for science now. And for us in this domain of material scientists, and especially us who are doing the modeling simulations, we have a window of opportunity here that it will be good for us to be able to explore. And in order to do this, we need to design sovereignty. And the reason why I'm saying we need to design to do materials innovation with sovereignty is because if we have these supply dependencies that are plagued on these global value chains, there is a likelihood that no matter how good we do our work, no matter how well we model, no matter how well we innovate, we still have the bottleneck that is going to control us. But then when we look at tech power dynamics and what technology is doing to the innovation landscape, we see that even in the materials discovery space, we can be able to evolve this field. But the challenge that we have here, if we look at the status quo we have here in the state of the art technologies and applications that we are using, we are saying that the way we discover materials today is most of our ideas are hypothesis driven, whereby we are saying that perhaps if I dope this material, I can improve the property of this material, or sometimes if I create a super alloy, it is going to be able to do this. And all of these things, we are doing it in a constrained system whereby we find that our labs are constrained in terms of funding and capacity. And then this leads to us having a very narrow exploration window, because we have to make what we call smart judgment, but when deciding which experiment to run. But when we do this, we put an implicit bias into testing our hypothesis. And then on the other scale, when we look at the state of the art tools that we have, so here I'm mainly concentrating on the theoretical, the people who are doing modeling and simulations. We find that the technologies are there, be it TFT. You will find that even no matter how hard we have been scaling it, we are still constrained by the compute power. And we have come up with even higher throughput pipelines that can help us screen material configuration space. But even when they do that, they improve our efficiency, but they don't improve our exploration space. So we need to find a way of having some form of automation or automated lab that are imbued with a little bit of intelligence so that they can be able to do, because what we are currently doing now, it is like we are just computing and computing more. I'm sure most of you, the materials modelers on the session today, I'm sure some of you have left a calculation still running somewhere. So we are still computing. But computing does not mean more discovery, as you will see in some of the slides that I'm going to have and this is why I'm saying it's like we are optimizing a pipeline without questioning the system, because like we believe that the system is okay. So now what we need to do, we only need to make the pipeline much better and improved and something of the sort. So what happens when optimization backfires? And I'm sure some of you have fell into some of these traps that we have, because first of all, what constrains us more, the only way we can show that we are doing serious work, or we have discovered a nice functioning materials in the lab, it is because we have been incentivized with publications, because everybody needs to publish, or when we say publish or perish and whatever. And we see that this one in itself has constrained the opportunity we could have explored. Because imagine if Vasco da Gama was going, when he was trying to explore the world, he was only going to ports that have already been discovered. Was it going to be a discovery anymore? And when we say now materials design, discovery, and innovation, these are some of the things that we are going to do. And I'm talking about systemic pathologies here when it comes to materials innovations, because these are the things that have really constrained us. And one of them is what I've mentioned. It falls under I normally like the Cobra effect because of how it functions. Because we are told that when the British went to India, they encountered the cobras. And because cobras were biting and killing most of the people whom they had come with, one brilliant gentleman decided to tell the locals that I want you to help me catch and kill a cobra. So for every cobra that you catch, I give you some money. And then over time, of course, because people knew this is a way of making money, the Indians used to bring so many cobras. But by doing that, the population of the cobras decreased. Then now what happens to the people who dependent on the cobra for their livelihood? They started now breeding cobras. So now they breed cobras, and maybe one cobra can give birth to even 15 cobras. And then it came to a point whereby it is not sustainable to be able to compensate everyone. And this is what we are seeing with the publication side. We are seeing now people even deciding, well, before it was a paywall kind of publication system, people are advocating for an open access publication system, because you find like in that one now you have to pay. Somebody must pay for that. And for us on the continent, we don't have the 2,600 Swiss francs that we need to publish open access. So you see, like now we are there. And then we have the tragedy of the commons. The tragedy of the commons is when one person gets benefit, everybody wants to copy this person. That is why we are seeing a lot of labs, like people working on similar projects. And because we have this kind of siloed approach to thinking, everybody wants to reach on the finish line fast. So we end up restricting ourselves to local optimization. Like if we are looking for a material that can be the best catalyst, everybody's trying to dope the same material in the same system, but we say I'm doping it in a different way. Then now everybody argues that my technique is the best, but then after that, which one is the best? So some of these effects you can be able to look out later, like the Hydra effect, whereby when you cut one head, two more heads emerge, and then the butterfly effect, whereby we want to be very concise in trying to make small choices that are going to yield big impacts. And then we see like these bottlenecks are some of the things that are happening because we are trying to optimize a pipeline, but we are not trying to innovate the discovery space. So this is where myself, around, it is now almost 2 years, I decided to shift my focus now, because I had already grown up in the DFT world and the materials modeling world, the calculation of the phonons and the band structures and whatever. I was trying to say like now, because this technology called artificial intelligence is here with us, and many people are using it for this and that, for this and that, and then looking on the African map, trying to find people who have been trying to do or who are trying to do in this domain. It was much of a struggle for me, because we were still also in that era whereby we were trying to do some reinforcement learnings, when we are trying to predict some materials, this and something like that. So I decided to look at it from this point of view, that every successive industrial revolution was informed by the tools that were available in the previous evolution. So now that we were in the era where compute is fine, the data is there, and all stuff is, and now we have also the artificial intelligence is coming to the fore. Is there a way we can use these techniques now to inform materials discovery? Because the periodic table is vast, the permutations we can have when we want to mix these materials using is a lot, and the applications is enormous. So what if we can be able to apply this? But then the AI technology is not a magic, or it's not like a magic bullet where whenever you have a problem, you plug it into AI and voila, you are able to do that. So there has to be pros and cons to any technology that we are currently deploying. So like for us, mainly what we try to do is mainly to use AI in trying to discover properties of drugs and medicines and active sites in polymers and the folding of the polymers and some of the sort. But we have to be sure what AI can actually do. Because just as when you go to the job markets or you are being hired for a position, you have to put in the CV. AI also has its CV. So many people try to ignore the CV and say, AI is smart and whatever. And what people don't know that AI, it is just a model. It is just a machine that is dumb, and that is why we have to train it. That is why we call it machine learning. And then when it becomes smart, then we give it the intelligence. So AI excels at predictions, pattern recognitions, and also probabilistic reasoning for them to be able to decide which one is in or which one is out. We call it inclusion and exclusion criteria. But then we have to make a distinction that by AI being able to predict it does not mean it has discovered, as I will be showing you going forward. So if we look at these materials and discovery value chain, and we try to map out where AI sits today, we are seeing the emergence of two architectures. Because you see, what we're trying to do is it is a creative collaboration between man and machine. And when it comes to materials, we normally say we design, we make, we test, or we analyze. That is for us who are doing in silico calculations. But for those people in the lab, they will say you hypothesize, you synthesize, you test and evaluate, and then you analyze. So the cycle, the innovation cycle is the same. But then now we are starting to see architectures that I will also explain going forward of AI plus human, where we are having what we call HITL, the human in the loop kind of approach, whereby even though we are allowing the model to run, we are still imposing constraint onto the limits. We are trying to we are giving the model a road that it must follow. And then we are giving the model the rules of the road so that they know here I need to turn left or here I turn right. Here I need to stop and go. Here I need to wait and something of the sort. But the architecture that I see emerging and that I'm currently exploring is whereby we have AI scientists and AI assistants that are working with the human being, And for this, we are looking at, I started by checking on the different advancements so that I can be able to know the distinctions of what I can use. Because we normally have bots, we have AI agents. I'm sure everybody has heard of a bot. Everybody has heard of an AI agent. We are new terms are coming in now called agentic AI since the discovery of AI agents. And after agentic AI, we have what we call the mixture of experts, whereby you have many agents that are doing different parts of the things, and then at the end, they consensualize their output, and then it becomes one big output. So if you look at the level in AI advancements, it starts from the one that is done to the one that is called like a clever, or that is called like an expert person. But then you see, as I had said previously, that we are talking about prediction, 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 prediction. And I argue here that it's like you are climbing faster, but on the same hill. Like you are not changing your terrain. It is just that you are doing what you are doing within your terrain better. Maybe because you have legacy memory and something like that. So if we train, like let's say, an agent on an AI model to determine the best dopant. So it will be too mechanical because you will give it the list of dopants that you want. Maybe you start with zinc, then you go to titanium, then you go to vanadium, then you go. So you supply a list, and then you see. And then over time, AI will be able to know using the probabilistic reasoning that they have that maybe if I put in scandium inside there, scandium will not work. So it will definitely throw it out at something of the sort. So when I say we are climbing faster on the same hills, it's like the way we do discovery now. We like to do, we need to do distortions or to introduce something into the materials, and then we check the impact of what is happening from the norm. So it means that we have a norm that we want to see if another dopant is going to disequilibrate from this norm. So you are starting to see there we are starting from a safe space. You see, so because we are starting in a safe space, it means that we have imposed a criterion that this one is the best. So because this one is the best, I want to know which other one works better than this one or works closer than this one. And we see it also like when it comes to polymers. It is because like polymers is about chains and side chains and chain reactions. So we will try and see it's like, okay, what if I put this one in the side chain? What if I cut it off? What if I do this and whatever? Or sometimes we tweak the rotations and something of the sort. And because it is not humanly possible to do all the rotations, we normally believe like AI can be able to give us the best. And then the other one we normally do is like what we have in alloying, whereby we start by combining non-coexistent, like we say, like which is we say an alloy of copper and zinc and whatever. And then when it comes to catalysis, we are trying to look at if we put in some dopants on the surface and something of the sort. So the challenge that is there, it's like it gives us this hype. I'm sure if you go online now and you look for papers that have either used machine learning or claim to do AI on materials, you'll see it's like it will be telling us, we have a very good material. This material is fine. Our model it performs better, outperforms the other one, and whatever. But you see, because it was only predicting, you need to know that the AI will only be as good as the model that is being used to train. So it will be very good to tell us what is likely given what we already know. You see, but what happens within the coming on? Because the AI tools that we are using now to discover materials, they are more predictive than generative. In that, in that, like for them, they are using learned patterns because they were trained on existing databases. And that one is normally a very good place to start. I'm not telling people who are working with AI now don't go to materials cloud and whatever to get your stuff. No, 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 no. I'm just trying to see the weaknesses that are there. And then after doing that, we go to the human validation part because, like somebody will say, how did the model? Well, so it means that a human being already has an idea as to what a material is, and then the AI answer the question right. But then with this process, we find that now novelty sometimes can be filtered out. It is not the science that is filtered out, but novelty, because if the human has to decide, then the lab can only synthesize that which was decided. But in doing this, haven't we excluded a huge body of knowledge out of the known? So we need to venture into the unknown. Because what if the next material is not in our databases? But it can also be that simulations have not yet found it because we restricted the calculation. And this now brings me to the symbiosis between you as a scientist and the tools that you have. For me, in my case, it is the case of AI, because great scientists never worked alone. If you look at Marie Curie, she was an understudy of Henri Becquerel. Charles Darwin was also an understudy of Adam Sedgwick. Lars Pauling was also an understudy of Frank Gehry. All of these people, like it was a good scientist. These understudies even ended up becoming better scientists than the people that they were they're doing the apprenticeship with. For example, like Marie Curie ended up even having 2 Nobel Prizes, while Henri Becquerel only had one. You see, so we see that now. It means that the way you can win the innovation game is having the right partners around you or the right apprentices around you, because they are the ones who can also help you push you up as you also be able to push it up. So I want to ask you as a material scientist here on this call today, who is your Marie Curie? I'm sure some of you are lucky to have met their Marie Curie in the course of their research. For some of us, we are seeing patches of Marie Curie in some of the things that we are able to do. But now, because we have to win this materials innovation game, what can be our greatest advantage? If you look at the materials discovery, it is more like it is a complex adaptive system, in that it is not only one part, it is not only the experimentalist or the modeler or the coder or whoever that is able to do all these things. And that is why for me, I started borrowing from economics of the two-sided marketplace, whereby now in a two-sided marketplace is whereby you have a buyer and you have a seller. You have a seller and a buyer. And then the seller and the buyer, they want to haggle over the price. I'm selling it for this, and then I don't sell it for this. But then, okay, if I'm buying it at this price, can I also have that one and that one? So you see some aspect of negotiation. And when everybody wants to buy something, there will be this competing interest in that. Like me, I want to take this, me, I want to take that, and something of the sort. And here is where I normally say agent-based discovery is a very novel idea, because what it can do is that you can have an agent, the agents that are debating and negotiating with them, you don't restrict them. You let them run amok with the idea. So like now, we don't ask the question that which is the best material according to the model, because that is what AI is doing here. Which is the best material for photocatalysis? Which one is the best material for solar cells, for example? So we need them to ask the questions. It's like, what materials can emerge when we have many scientists working on the same thing? Like, we just let them discuss. And then we find that now discovery now emerges from interaction and not optimization. So we are shifting from the optimization domain, and now we go to the discovery domain, and then we tell them, try anything. And then come and tell me, what did you go find? And in this now, you can have something like this, agents as virtual researchers, whereby now you have an ideation agent that it generates the material ideas and something of the sort. So on this talk today, I didn't talk of the techniques that we use for building these agents, like LLMs and knowledge graphs. We know what we use them for. Then we have PINs, the physics-informed neural networks and stuff like that. So you can have like an idea agent that just gives the hypothesis after studying all the information that is known. And then you have somebody that can be able to analyze for your behavior, then the other one that will synthesize, the other one that will evaluate, and then the one that tests. So you have all of these five scientists or virtual researchers debating amongst themselves, because everybody has their role and their function in the ecosystem. And then after that now, at the end, you will get a recommendation that after all these debate we have had, we think that this and this can be a good idea, and you can synthesize it in this manner. That is the vision, or that is the dream that I had already hypothesized. And initially it was very ambitious, but so far we are seeing the emergence of what people are calling self-driving labs, autonomous labs, and whatever, and they are actually anchoring upon the same philosophy. So in this instance now, we find that now materials discoveries phase, the agents that are doing the discovery, they will be looking at several other dimensions that you, as a single scientist in your lab, you will not be able to do it. I'm sure some of you who synthesize materials, sometimes you make the material in your lab, you send it to another lab to analysis, and then you bring in your results, and then that is when you publish. So here now we want novelty to be the currency, in that you hit the right spot at the right time, and then we are able to see how well we can evolve. So I apologize, we are almost about to finish. So I'm not saying that this methodology of agentic science, that it is foolproof, that everything you will get from there is actually the right thing. Sometimes also, because we are the ones who are designing these tools, we can also design tools with implicit bias inside it. Like, for example, you see the difference between OpenAI and DeepSeek. You find like in DeepSeek, there is implicit bias against the government of China, in that you cannot find anything negative no matter how much you prompt it to do it. So still that one can also be imbued in some of these things. So we can have like biases also in these loops, and the discovery that we are only to get. Sometimes we can get materials that are just illusion, confirming what we have now. How many DFT results are out there that have been confirmed using experiments? You see, so there is still need for the human role in all of these things. But now your role is not mainly to predict, but to be able to govern. Because blind automation is also equally as dangerous. And when it comes to governance, we have three main control regimes. We have what we refer as the human in the loop. This is whereby you, as a scientist, you approve every AI decision to make sure that it is safe, it is operating within the limits it has. And then we have the human on the loop. So when the human is on the loop, it means that you, as a scientist, you set out your constraints, and then you allow the agents to explore themselves freely. And then we have the human out of the loop, whereby you let the things to be fully autonomous. So these are some of the constraints that we can be able to apply. So I want to end here because of the interest of time. I have a couple of case studies that I believe that by the time we will reach Nairobi in December, we will be able to discuss more. But what I was trying to do here is to ask yourself, what if you had the ability to do more than you are currently capable of doing by leveraging AI and AI agents? Thank you for listening. Over to you, Victor.
Thanks a lot, Cecil. Thanks for this insightful talk. And I'm sure we have a number of questions or comments from our participants. And I note that you started by telling us that we should reclaim our inheritance. Mathematics started from Africa, and therefore we should reclaim that and do the maths. And you've also noted that in some years' time, by 2050, most of the youths will be in Africa, and therefore we should take advantage of that. I'm just trying to to give some summary or the highlights of your talk. And one more important one is that we should move from prediction to discovery. So prediction is not discovery. Most of what we do here is to predict computationally, but we need to move from that phase of prediction to discovery and move from being operators to governors of discovery. I'm just trying to summarize what you have said. But with that, I want to welcome our participants. Anyone with a question, comment from the presentation? Anyone, if you have any question, feel free to raise your hand or you can unmute your mic. I have a comment from Professor Moboro, who is requesting that you share your presentation. Okay.
Yeah,
Anyone?
definitely. Definitely. I'm going to share the presentation.
Thank you. So as we wait for the questions, I know you've done a lot of computation. I know you have mentioned that great scientists were never alone. And I'm trying to see the picture of experimental scientists. Do they seem now not to be moving in the right direction, given that AI can predict and even do the discovery? The agents can discuss, can have a debate and come up with probably a better solution. How would you advise experimental scientists to conduct or the direction in which he should do his work from a computational point.
Okay. That one is a tricky one. But over the years, what I've come to discover is that even experimental scientists, it reaches a point whereby they need to analyze a graph, or they needed to plot an XRT graph, or they needed to maybe look at the data set that they have to be able to come up with maybe a spectra or whatever. Already there is a form of automation that is happening in the background that is making that line look that beautiful in itself. There is still the human part when it comes to the experimentalists, like the aspect of like loading the sample onto the device and then running the test and something of that. Already I know people, especially in South Korea, no, in South Korea have already started doing, whereby they have a lab that whereby it is robots that are doing everything from sample preparation all the way to the rest. But then for these robots to operate in this manner, it must plan the process to be able to be done. So for me, I believe AI is a good tool. It is just that I normally say AI, it's like fire. In the hands of an arsonist, it is dangerous. In the hands of a chef, it is very productive. So we have first of all to know which aspect can AI help them in guiding them. Already, see, when I joined computational material science, even during my master's, there was a lot of contestation between computational versus experimental. But then over time, we are starting to see, thanks to the materials genome initiative, we are starting to see collaborations between people who are doing modeling and people who are doing experimental synthesis. One of my students actually did both. She did both experimental and modeling and was able to join the two analysis together. So for me, I believe that if the experimentalist or this person who is synthesizing the materials needs to save on the samples that are being bought, because some of these samples are very can be expensive, I believe AI can help them come up with the right way of optimizing the experiments that they are running. Thank you.
Thank you, Cecil. There is a question from Tewodros Ayob.
Mm-hmm.
The chat, it says, it was great presentation. Thank you. The question is, AI-guided synthesis of materials has been known currently. How far has this gone? So he's inquiring on the status
Yeah.
of synthesis of materials.
Okay. So to the best of my knowledge, in the global north and on the global south, they have the self-driving labs already that are happening. In Africa, we are yet to set up one. So it is still there. I can say we have lab scale. Can I call it the lab scale? We call it like the preamble is already there. Like we have concepts. Yes, let me call them concept labs. We have concept labs that are already there, but they are mostly in the global north, and we may or we may not be able to maybe see how well they function. That is why for us we normally say, what if we also try to create one and build one? Won't it be something that also we can explore? But I know it is already there, already in the global north. And a couple of papers, if you Google self-driving labs, you'll see most of them are already there and they are working for different materials applications. Thank you.
Thank you. Anyone else with a question? Anyone else with a question? There's a question from Ngong. And the question is, how do you stay updated with the fast-paced advancements in AI and hardware?
The easiest answer to that is a student interacting with students and also sometimes attending AI-related conferences that are not actually in the material science domain. For example, the marketplace simulation that I saw, and I wanted to apply because it is like a game theory kind of application. It came out from Frontiers in AI Applications kind of conference that was organized just next door to where I was. So I went in and I was able to interact with some of these ideas. So for me, I normally say with the generation that is here, this generation of TikTok and whatever, you will find that for them, knowledge is not interdisciplinary or transdisciplinary and whatever. It is like a complex web of interactions. So that is how I believe that the youths of the future will be. For us now, we are existing in our domain. Either I am a physicist or a mathematician or a computer engineer and whatever. But then we have seen this tendency that is coming up that sometimes you are trained as a physicist, but then you do a PhD even in computer engineering. So we are going now to knowledge domains. We will no longer have these boundaries whereby we are categorized based on all of this. So the easiest answer I can give is interacting with people outside your domain who are working on AI, but also having students also who are interested in novel applications of AI. Thank you.
So just like what you said before, great scientists were never alone. So that means we need to have more interaction to know what is going on. There's another one from Theodros, from generative AI, e.g. ChatGPT or Gemini chatbots. Which one is the best to refine the DFT code? That is a bit specific.
Yeah. Okay, so on that one, I will refer to my second last slide. It is either you are doing human in the loop, human on the loop, and human out of the loop. I don't believe that generative AI can be able to refine the code. What we need to use AI for is to bounce ideas on how we can be able to maybe optimize the implementation of a DFT code. You see, ChatGPT and Gemini, they have been trained like in almost all the different knowledge, from astronomy to religion. So if you want it now to be very specific to do a task for you when it comes to something like DFT, it means that you have to teach it. Yeah? You have to teach it what you want it to do. Okay. And I know, like, especially when I was saying the agent that's used for discovery there, I know of people who build like a chatbot on top of ChatGPT on morphs to give them like prediction on like which one is the best morph for this application. For direct air capture, I want a morph that can be able to do this. So that one like that. So you have to train it. I'll tell the person who asked the question. You have to train your model because remember ChatGPT is a model. It is just a generative AI model. Gemini, the same. Okay, so it depends on what you do. People who do coding, they like using another generative AI called Cloud. It has been good for coding. There are people who use Grok, for example. So it is for you to teach, but first to teach it how to do it. And for you to teach it how to do it better, you must learn what we call prompting. Prompting is a very important skill to learn if you want to use this generative AI kind of applications. Thank you.
Thank you, Cecil. Oh, there's another question. Do you have knowledge or open to collaboration on how to use AI to monitor carbon dioxide conversion using novel heterojunction photocatalysts?
Okay, so for me, I welcome you to collaborate. I will like to know, especially what you want to find out and how you want to find it. What you want it to do, it is very specific. So that one might require the mixture of experts kind of a mixture of experts kind of approach. On the continent, I will say currently I don't know. I have no idea, and that is why I'm even interested, and thanks for the invitation to come for the African Materials Science Society this year, because maybe from there we can be able to bounce ideas along possible areas of synergies and collaboration within this domain. And that is why I was saying we should not be just be climbing the same hill effectively. we need to find a way to discover that there are other hills, or maybe we don't need to learn how to climb. We need also to learn how to swim. So maybe I will welcome for the collaboration. If you have my email, you can reach out and then we can be able to discuss more. Thank you.
Thanks. I'm sure you'll share your email in the chat so that interested participants can be able to reach you. So I have a question from Ngong. I'm not able to get it clearly. Ngong, are you able to unmute and ask?
Can you hear me?
Please go ahead.
All right. Anyway, I'm an experimentalist, so I'm coming from the chemistry side of materials. So my question is access to materials. So this is perhaps from an experimentalist point of view. So I'm calling from the US right now. So I'm just wondering, like the access to critical, materials is very, very important, and we have a lot of them in Africa, and navigating with the government, it can be quite tricky. Do you have any general comments on that?
Yes, thank you, Ngon. That is why I was saying when I was giving the picture, the panoramic picture of 2050 Africa, when we look at all of these gadgets, which material will be used to manufacture these materials? And the current materials we have, the ones we have or the ones we know, are tied in lots of geopolitical bottlenecks and scarcity constraints. That's why I was saying materials is leading wars now. And I was showing the picture there of people looking for jobs. One person is looking for food and the other one will have to be looking for material. It is because of that. And with this agentic ideology that I'm trying to posit here, I'm trying to say it's like, who decided that this material is critical? Maybe what is critical now might not be critical in 20 years' time. Because you might find that because somebody has imposed scarcity onto a particular material, people can innovate in other dimensions, such that these materials that was made scarce ceases being scarce, and then people move in that other dimension. You see, this is what I'm saying, like we need to try and explore, because currently our configuration space, we are restricted to these narrow kind of definitions when it comes to materials innovation and invention, whereby now we take, like, we know, like, let's say platinum is going to be scarce. Now we are saying, okay, can we take a little platinum, we put it on top of another material so that, we save on cost, we save on the rate of depletion and something like that. So with this kind of marketplace question I'm trying to ask here, what if these agents say, like, now, we don't want platinum anymore? Which other things can we discover? Because we need a material that can do ABCD, 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 and then it recommends. Okay. So the reality that we are in now, we are constrained within that domain. But perhaps we need to go beyond the hill and see if we can be able to do it. Hence the hypothesis I'm positing here today. Thank you.
Thank you very much.
Thank you. I guess a number of other comments, people sharing their contacts. So Professor Cecil has shared his email address there. But before we close, Cecil, in your own view, what is the uptake of AI in material science in Africa?
Yeah,
are you moving into it or dragging?
No, we are still playing catch up. And that is why, for me, I have elected to be deliberate that every student I'm getting from now on has to take an aspect of, like, let's say, an AI-driven kind of approach to research. So you will find that today I didn't talk about the different technologies that are there, but we have things we call physics-informed neural networks that can be used to optimize fuel cells. We have the large language models that we can use to generate some of these contents, especially protein value chains. We have the knowledge graph. So, and all of these other ideas. So the uptake is still small. And the reason why I went into this field is because when I was looking at what people are doing outside there and then trying to check who in Africa is doing all these things, I didn't find like a lot of people, I didn't find people doing it. So we are still way behind, but I believe we have an opportunity for catch up because we have a lot of these youth that are coming in with this new renewed energy. And I believe that if we channel the right knowledge to these young people, then we will have that multiplier effect when it comes to people that are going to embrace this technology. Because you see, mainly in our continent, we are in the show me kind of space. People don't like to imagine beyond. Yeah, we are in the show me. Somebody wants to see, like, okay, so and so has been working in this, then yes, I can be able to. We can be able to do this. But at AIMS, there is this kind of creator concepts whereby we are saying test the limits of even like mathematical, like if a plus b is equals to c squared, it is okay. Just show us why it is not, and then we see how well to do it. So we are still playing catch up, and I hope we will be able to adapt going forward.
Thank you so much, Cecil. I wish to remind our participants that we shall proceed on with more of this discussion during our conference, the AMRS 2026 in December from 5th to 10th. AI in material science is one of the themes, so please register and come. We have more of this, and Cecil will be there and many other experts. And with that, I want to thank you, Cecil, for your time. I know it was on a short
Pleasure.
notice that we invited you, but I want to appreciate you for coming and talking to our participants. And we hope to interact more with you and with everyone who is here because discoveries come from interactions. Thank you and
Thank you.
goodbye,
Thank you so
everyone.
much, Victor. Thank you for the invitation, and thank you everyone for listening. Thank you.
Okay, thank you. See you next month for our next webinar. Goodbye.